the networking opportunities here at CppCon are well above and beyond any other C++ conference that I've ever been to.
Welcome everybody, hello. My name is Nicolai Josuttis, and I have the honor to talk about iterators, something I think I first did 30 years ago. It is that C++ is, well, a big part of my life, as I've written a couple of books about it and giving trainings a lot of times. And I was also involved in the C++ standardization, and I still am. So it's partially all my fault. So here in this talk, we want to get back to basics because, well, over the years, it hasn't become easier to learn C++. So basics, which is we have to talk about iterators, which play a key role in C++. It's probably one of the features that made C++ a success story. So when we loop over an array, the usual thing we learned in programming was you can use an index. So we can use some index counting here from 0 to 3, and then print the elements in this array, which you see there on the right. But there's another way to do that. And this other way is already available in the programming language C, which is you can take the addresses of the elements, so-called pointers, and the array itself can be used as a pointer, and array plus 1, 2, 3, 4 are the next 1, 2, second, third element. And you can initialize a pointer with the array and then iterate over the array until you hit the end. As I said, that's already available in C. But it was the basics of an idea that we want to abstract this idea, not to be able to iterate over elements, even if they are not in an array. Please note that the last position, the position I compare against, is valid to use, although the element, the value there, is not. There's already the next object starting. So don't use that memory. If you use that address, array plus 4, that's fine, but don't go to the value there. That's an important principle, which we will also find in iterators. So iterators are an abstraction of this idea. So if you take this idea to iterate with a pointer over the array, let's do and try to be able to do that everywhere. Let's do that in a vector, for example here. But how do we define the address of the first element and the address behind the last element to write the same code? Well, we introduce some member functions, and these member functions are begin and end. So by asking the vector where's the beginning and where's the end, we can do more or less the same as we can do with the pointer. We can use something that is able to iterate over the elements of this container. It has its own type. In this case, it's an iterator type of an std vector of int. We will see later on why we have different type or specific type for that. So same you can do, for example, for a string. So we have begin and end also there defined, and we can use an iterator. We get it with begin, and we iterate as long as we are less than the end. Go always to the next element, and if we need the value, we use the star operator. Good. So far, so good. That was the beginning 30 years ago. Now, these days, nobody writes that code. That's far too much typo, characters to type. So let's use auto here. In general, it's not the recommendation that you use all the time everywhere auto. but more and more we do, especially if we don't care for the exact type. We know that with begin we get an iterator, and what the exact type is does not really matter. So here auto is a perfect example for useful application. Please note that we still have the principle here that the end is not an element, or at the end there's not an element. It's a position right behind the last element. So why? We say this is a half-open range. It includes the begin, but it does exclude the end. So why did we do that? Why was that designed that way? Well, first of all, the consequences, as you have seen before, you can use the end position, but not the value there. Don't do that. That's undefined behavior. There is something, but you never know what it is and how it behaves. So why do we have that? With that, we don't need special handling for empty collections. So in an empty collection, begin equals to end, and the loop you see there still works. We initialize with the begin while we are less than the end. We iterate over the elements. Well, we are immediately equal to the end, and so this loop does nothing and works for empty collections. Okay, now you've seen the principle of what is an iterator. Why do we have them? Here's an example of one container we have. A container is kind of a data structure we have in the C++ standard. So we can put there many elements, and they are stored in some way. A vector stores the elements in continuous memory. So as you see here, we have a core object where we know the size, we know how much memory we have allocated, and we have a pointer to the real raw memory where the elements are stored, which is usually on the heap. That is where you get your iterators from. So when you start to iterate over the elements of this vector, you are pointing, you are referring right inside this vector at some specific location. So when we now ask this vector, give me the fourth element, that's a cheap operation. Why is it cheap? Because how we use that is we go to the begin, and then we advanced 4 elements, which we can compute easily because we know the size of each element, and as all elements are in continuous memory, it's easy to compute where the element is. But we have other data structures in C++. So one other data structure is a linked list, a doubly linked list. It's called std list. So here, it's not that all the elements are in continuous memory. Here it is that each and every element tells you where you find the next element. Each element has a pointer to the next element. And by the way, each element also has a pointer to the previous element. It's a doubly linked list. Using a list has some benefits, which we don't have to discuss yet. It's just one of the data structures we have. Now think about, we would try now to use the index operator here to access an element. That would be an expensive call, because we cannot compute where the third or fourth element is. We have to go to the begin, to the first element, ask where's the next element to have the second, ask where's the next element, where's the next, and ask where's for the next element to get the fourth element. That is an expensive call. And you know what? One reason we do C++ is because we don't like bad performance. So, what is the consequence? Well, don't do that. We could do don't do that. We could say don't do that. But in this case, we want to protect you from yourself as a programmer. So we decided we don't offer this operation. Especially as If you iterate with an index over the iteration, what happens is each time you use the index operator, you go to the beginning and then you find your element. The first time it's only begin, the next time it's begin to the first element, the next time it's begin to the first and second element, and so on and so on and so on. So finally, if you have 1 million elements, you call begin and then 1 million times follow a pointer to find your element. That would be a nightmare just to read, access the elements. With an iterator, it's better. With an iterator, we can start at the begin, knowing that we iterate over the elements, just follow all the time only to the next element, go to the next element. So this has significant better performance. And that is the only portable way for all our data structures to iterate over all elements. So the basic way to deal with all elements in some data structure is call begin and then start to iterate with what you get back, as long as you are not at the end. For the next element, you call plus plus. For the value at this element, you call star. That's the basic heart of everything in C++. As soon as we deal with collections and data structures. And that is obviously a perfect example for a function template, because this function template would compile for all the different types we have. You see on the right some types we have. You saw already vector and then doubly linked list, but we have even more complex data structures like balanced binary trees. On the bottom right, you see hash tables. They all work with this API, which means, as it is a template, we don't compile this code in a way that we have a generic pointer finding the next element. It's generic code that once we know for which object, for which collection we call this for, we compile this. So for example, we compile peer in the first call of print elams. We compile print elams for an std vector of int. And the interesting thing is that the plus plus operator here is specific implemented for ints that way. It will just go ahead to the next memory, adjusting the address by the size of an int. If you then instead use a balanced binary tree, which we have here, it's called a set, then what we do with plus plus, we navigate to the next element, which can be pretty complicated. The next element is on the right subtree, the leftmost element. Or if there's no right subtree, we have to navigate up and take that element there. So that is essentially what happens if you call plus plus, which obviously makes plus plus a little bit more expensive. But the point is, we can easily iterate through all these data structures with the same code. And as we have templates, instead of one type doing everything for us, we decide how to iterate at compile time. And that means compilers can optimize at compile time. So they can see the way we iterate through this data structure, like a balanced binary tree, and optimize whatever they can to make our code as fast as possible. OK. So this is a way we iterate through all the containers. There's a shortcut for that available since C++11, which is the range-based for loop, which we could put in a function template. But under the hood, the range-based for loop does exactly what you see above. So the range-based for loop calls begin and end to initialize an iterator to iterate over the elements until we are at the end. In C++20, there's a new way to write that. Instead of using a template parameter, you could write auto here. That's only syntactic sugar, very nice syntactic sugar. You could also constrain this type in some way, saying this has to be a range to improve error messages. But again, this is syntactic sugar. At the end, you're using iterators to iterate over all your elements of the past collection. Sometimes we care in C++ for const this. So we have a keyword called const. Well, why did we have it? It's not to make your life hard. It's to help you to find bugs at compile time. So the keyword const helps us to say, it's my intention not to modify anything. And with const, you can protect yourself that you not accidentally modify things where you don't want to do that. To support that idea, if we iterate over the elements, even if the container is modifiable, we introduce the type for each and every container class, which is called the const iterator type. And by definition, that means if you access the element, it's const, which usually means you cannot modify it. You can screw that up in C++. So that means if you try here, for example, to assign a value there, that will not compile. We also have support for auto here, because if you want to use auto because it's so much stuff to type to declare the exact iterator type, then, and we still want to have a const iterator, we introduce something called cbegin and cend. It's just a helper to make sure that if it's working like begin and end, but returns a const iterator. So it has the same effect. You protect yourself from not accidentally modifying the elements. This, by the way, is partially broken by C++20 and 23 views. Be careful a little bit with that. I don't explain that now. Now, there's one important thing to learn here. I told you already that we want to protect you from doing something bad regarding performance. And that applies, for example, by not having the index operator available unless we can directly jump to an element, which we call random access. We can randomly access to the 100th element, for example. We do the same for iterators. We protect you from doing something with iterators which has remarkable bad performance. And for that reason, we have different categories of iterators. Iterators have anyway different types. But we categorize these types in a way that we say, with some iterators, you can do more than with others. So one category is a random access iterator category. And as the name says, it allows random access. You can jump directly to another position. For example, we support plus equals. Plus equals, you can say plus equals 100, and that means advance 100 elements. And we provide that because for the containers we provide that, we can compute where this element is. For example, in a vector, we know where it is. This is not the case for all the other containers. In all the other containers, we cannot compute where the 100th next element is. We can only 100 times go to the next element. So as a consequence, we say, well, these iterators, if you iterate over these data structures, they cannot do plus equals. And there are a few other things they cannot do. For example, you cannot call less than. You cannot easily compute whether one element is before the other. which is easy if we just compare the addresses. But a linked list, in a linked list or in a tree, the elements can be spread all over your memory. So there's no way to easily find out whether one element is in front of the other or compute the distance between two elements. That's all not supported. So if you still can go forward and backward, it's called the bidirectional iterator. So, but there might be containers where you can only go forward. We have that for singly linked lists. They have no backlink in each element. And hash tables, by the way, also have only iterators where you can go forward. The reason is that in hash tables, they internally use linked lists. You see that there. It's an array of linked lists. And that linked list can be a singly linked list. So therefore, we don't have that bidirectional iterations there. There is, in principle, another category where we not have an obvious container for, which has an interesting constraint. In all these iterators you see here, if you are at a certain position and you have two iterators pointing to that position, and you advance them once, go to the next element, they find the same element. So we say they are equality preserving, which is not the case in an input iterator. Input iterator is a tricky beast, which means we have the interface of an iterator, but the way we use it is that we read, for example, from standard input. So if you have two objects of that, and they both use standard input, and one goes ahead one element, which means we read one element, and then the other goes ahead one element, they have different values because one reads the next element and then the next one reads the other next element. So they are not equality preserving, and we call them input iterators. So what this semantically means is you can safely read the elements only once. You might have to care for these categories in your code. So for example, this, what you see there on the top, is code that does not work, that does work with each and every container, because all the iterator categories we had, they provide this minimum set of operations, the blue ones. Guess you want to print every second element. And you can start with this code. This code is a little bit more complicated, and it's not that easy as you think at first. So you initialize your position with the begin, and then let's iterate with plus equals 2 each and every time. Well, I told you plus equals 2 is only available for random access iterators. So therefore, this will not work for other containers. But there's another reason why this does not work. It's less than. So because we have to deal with the problem, we might jump over the end. So we go to the last element, and then we call plus equals 2, and we jump over the end. We cannot use not equals. So we have two reasons we cannot use something like a linked list or balanced binary tree or a hash table. So that code, even if it's generic, does only work on a restricted set of data structures who have this requirement. We have a requirement here. We need a random access. Well, you can fix that. You can write this code differently. So you could make sure you only need the basic operations of all iterators. So you see we now switch to not equals. And instead of calling at the end plus equals 2, we call plus plus pos at the end of the body. You could also do that on the right-hand side of the reinitialization area. That depends on your style. The important point is to make sure that, because we only compare with not equals against end, to make sure that we don't jump over the end, we have to say, and when after plus plus, we are not at the end, let's do 1 plus plus again. So that way, we can iterate over every second element, but we still make sure we find at the end. Okay? Good. And by the way, what you just saw is a reason you should not use a less than sign here in this basic loop, because the less than does only work for random access iterators. So that is really the basic way to iterate over the elements. Just a hint here, iterator categories have changed in C++20. We have a new category. So there's a category called continuous iterator. And we have corresponding categories for the ranges we iterate over. So continuous range, random access range, etc. So why did we introduce that, and what is the difference? Before, everything above bidirectional iterator was a random access iterator. Now, for continuous iterators, we have a special group. And that means all the elements are in continuous memory. So the reason we have that is that for these iterators, we can do something special. So for example, we can internally use raw pointers because we know that all the elements are in continuous memory. Or we could also convert the value, the array, the internal list of elements into a raw C array by calling a data, a function like data. That's possible there. That's not possible for random access iterators, which don't have continuous memory. There's one example, exactly one, where we have that. It's called the DAG, because the DAG is internally using an array of arrays. So we can still compute where's the 100th element, but it's not just adding 100 times the size of something. With the 100, we have to see how many arrays do we have internally and divide by their size, and then we know which array to take, and then we can jump to the element. So it's still fast to find an element. That's why we have random access, but they are not in continuous memory. Okay, these are the basics. And with these basics, we came up with the fundamental programming model that made C++ a success story. We came up and said, you know, we have different data structures. We call them also ranges. We implement them as containers. And then we have algorithms that work on them. And instead of implementing all the algorithms for all the containers with all the different types, let's implement the algorithms once using the same API, which all the containers provide, which are the iterators. So iterators is the key glue code to bring together different data structures with different algorithms. So, for example, we have a sort algorithm. The sort algorithms, you pass begin and end before you came to C++20 at least. And that will internally sort the values of the elements. Sort, for example, needs random access because they jump back and forth between all the elements in this data structure. So sort will only compile and work when the data structures are random access iterators, random access ranges, or use random access iterators. Or better, I should say, since C++20, because we have the continuous category. Here's another example, max element. Let's search for the maximum element, which is a little bit funny. It's a generic algorithm that works everywhere. A set sorts the elements automatically, so there's an easier way to find the maximum element. It's the last element, but you can still call this, because in all the other containers, you might not find it right at the end. There might be none, so that's another reason we have half-open ranges. If there's none, we return the end position, saying there is no element found. Well, how can we not have a maximum element if the collection is empty? Yes. Here's a numeric algorithm. Let's accumulate all the elements and add them to an initial value 0 here. Here's how it is implemented. That's generic code using these iterators. So you see, accumulate takes at the top, begin and end. That defines the range, including the first element, excluding the last element, and then the starting value. And internally, we do what you just learned is, let's initialize an iterator, initialize with begin, while we are not at the end, go always to the next element, and add the current value to the existing value. So we can use that for a vector of long values, and we get the sum of all the long values in this vector. As this is generic code, it works for all the containers, for all the data structures, and for all element types, as long as the element types understand plus. So you can use it for strings. So just for fun, initialize a set of string with the elements 1, 2, 3, and 4 written out as spelled out as a string. And what is the output? Think a moment. What is the output? We start with an empty string there. So if you think the output is just one string having the value 1, 2, 3, 4 inside, that's wrong. This slide is a trap. Because set sorts the element. So the output is 4, 1, 3, 2, of course. But the principle remains. OK. Please note that in this principle, while we bring together algorithms dealing with containers and different data structures, using the iterators as glue code here, this works with the idea of pure abstraction. You will not find a base class for all the iterators. You will not find a base class for all the containers. The principle is everything that behaves like a container is a container. Everything that behaves like an iterator is an iterator. So what behaves like an iterator and can be used here is raw arrays. Or pointers, pointing into the raw array. So you could declare an array of doubles here, and then pass array and array plus 5, array as the address of the first element, array plus 5 as the address behind the last element. And that works, because what we internally do with this pointer is we call plus plus, we call not equals, and we call star to get the value, and that works. So that was a key element of this design. At that time when this design was developed, that was in 1998. Well, in 1998 we shipped the standard, so it was developed in the 90s. That was kind of a revolution in a way that we didn't follow the other revolution, because that was where everybody said you have to do everything object-oriented. And when you have everything object-oriented, you put together data and behavior and functions. And so, but we separated it. We say, oh, no, we have the data, and then we have the function, the accumulate. It's separated. So everybody said, you're absolutely crazy to do that. You didn't learn the lesson. Well, we learned. This is a different paradigm. This is generic programming, not object-oriented programming. And it was the beginning to learn that one of the success stories of C++ is that it is a multi-paradigm language. We use the right paradigm to program for the appropriate problem. Of course, we use inheritance, when it is important, which is not so often the case, by the way. Okay. There are caveats. There are pitfalls. There are traps. So, in other words, you can do something wrong. Let's look at this example. Let's use iterators of vectors. If you create such a vector, I told you already, it looks roughly internally like this. You have a size, a capacity, and the data pointer. And the data pointer is referring to where we store the values we have currently in this container, which is usually allocated on the heap. So that is what you get with this declaration and initialization. When we iterate over this using a range-based for loop, the range-based for loop uses iterators to iterate from begin to end. So the vector has begin and end, and that is used by the range-based for loop to iterate over the elements. And what you get while you iterate is the element. For that, the range-based for loop internally calls the star operator. So now let's find the first element with the value 8. We have 1, so we point right in the middle of this data structure. We'll refer to it. And please note that this also works if we don't have a vector, if we have other data structures like balanced binary tree or so. That code is generic. We refer with some type to some element in this vector. Now, vectors have a special ability. They guarantee that all the elements are always in continuous memory. Well, which is a problem when we add a new element. And we already have used all the memory we currently have. So the capacity, as we say, is equal to the size. So, oh, I forgot that. Before I say that, yeah, you can use that iterator to print out we have 1 and modify this value, for example, to double the value. That's fine to do. So now let me come back to the point and let's add a new element here. The vector needs more memory. To do that, the vector reallocates. And that means a couple of things happen. So first of all, we have to allocate more memory. Well, the vector has to do, which it does. By some policy, so they might double the size, or some other implementations add only 50% of the size. That depends on the implementation. We have no guarantee in the standard how exactly memory grows. So here we double the memory, so we have capacity for 18 elements. Now we need all the existing elements in the new memory, so they are moved, and the new element is stored. If these are strings, each and every string is copied or moved, because we no longer need it at the old location. In the old location, we can destroy them. And we can free up the memory there, which unfortunately is used by pos8. So if you now say, oh, let me modify pos8 by 2 again, multiplied by 2, that's undefined behavior. Well, this memory might now used by something else, and you modify this something else, which can create trouble, deep trouble. If you have a column, you're lucky, because you see that something goes wrong. It might just change your string with your key to encrypt the data or so, and that might be worse. And of course, only if you delivered it to the customer. Your tests work fine. That's a fatal runtime error, undefined behavior. It's your task to reinitialize pos8 or no longer use it. Why don't we do it automatically? Performance. There are other things that can go wrong. Look, for example, at this. This is a transform algorithm. It reads all elements from a source, transform them in some way. For example, here we square it. We can use a function, or you can also use a lambda there, and then write all the elements to a destination. Well, if you have that, there's some important thing to know. The writing iterator overwrites. The writing iterator writes at the location it is currently at, and then goes to the next element. This means if we compute squares from a couple of input values, there have to be room for the output values. Unless, otherwise, you have undefined behavior. So think about, you make the following. You say, my source has 6 elements. My destination is empty. That's a fatal runtime error. Again, undefined behavior. Here's the point. Your source has a usual begin and end. Your destination is empty. You call transform. You iterate reading from the source. You iterate writing at the destination. But there is no memory. You overwrite other data. Not a good idea. So, for example, what you could do is you can resize, not reallocate. Reallocate only allocates memory. Resize really means there are valid values which I can overwrite and say here, okay, let's first make sure we have enough elements to overwrite. Yeah, that's not the best way to solve it, but this works. That's not broken. There are other ways to do that. One other trick is to use a very clever special iterator, which is called an inserter, well, an back inserter. And now we come to the magic of this library. Everything that behaves like an iterator is an iterator. So what the back inserter does, it says, oh, you want to write a value, and then you want to adjust to the next value. So for me, you call plus plus, and then with star, you store a value. The API of this back inserter takes that to say, okay, you know what? If you call plus plus, I do nothing. If you then call star value equals something, I call pushback. Well, for that, I have to know what to call this pushback. So the back inserter needs, that is one iterator which needs the destination, the container. That is a trick to solve this. Okay, it's still a valid iterator, and we insert the values as they are. Finally, what is the output of this program? That's a third caveat. That's a collection. Let's print all the elements, which has these values inside. The 3s are marked because I want to remove them. And there's an algorithm that removes them. Let's remove these elements. Now let's print the output again. And let's print out the content of this collection. The output is this. To some extent, 3s are gone, but there are still as many elements as before. Why? Why? Removing algorithms using iterators cannot remove. Because an iterator cannot remove. All the iterator can is go to the value, read it or write it, and then go to the next value. Unless we have something special like a back inserter, which cheats with this API. So what we really do, what the iterators, what these algorithms do here, there is a reading iteration on the top with the blue, and then the writing iteration on the bottom. That is an outcome for the removal. And then when we hit the 3, we say, oh, let's move the 2 to the 3, and then therefore the 1 to the 2, and then the 1 to the previous one, and then the 2 to the 1, and then oh no, the 3 we want to skip. So the 4 to the 2, and the 5 to the 3, and the 6 to the 4, and that's my new end then. And let's leave the others alone. So the way this works, because we only can read and write and go forward and backward and jump around, that is the only thing we can do naturally. You can also not change the size of an array with a pointer. It's the same thing. Just pointing to one element, I mean. So, as you saw, there's support. You get the new back, new end, and all you do is you iterate then from begin to the new end and print out all the elements, and voila, you have the effect you want. Can we do better? Yes. This is basic. That's more or less C++ 98. If I have there on the right top, I try for each and every slide now to show with which valid it gets, with which version it gets valid, because we have so many C++ versions. So this essentially means this is contents of C++ 98. C++ 11 is only used because we use auto and for initialization with curly braces, some syntactic sugar. So yes, you can still use the range-based for loop with C++ 20. Because in C++ 20, we come up with ranges, with range support and views. And what you can create is something that is defined by 2 iterators but behaves like a range, but does not create a copy of everything. It just refers to the original data. So this is what we call a subrange. A subrange is kind of a view. We say, well, this is a range starting with begin, going to end, to the new end. And you can use this subrange as each and every iterator container. So you can call there, again, begin and end, and plus, plus, and it works. So that is another way to do that. Well, there's a third way to do that. If we switch to C++ 20, we can even make it even better. We can say, oh, let's not modify the container at all. Let's print out all the elements except the 3s. Or if printing is just an example, let's process all the elements in this container except the 3s. The way to do that is to use a filter. So you see this syntax? Very nice to use now. That is, a collection is piped into a filter, and the filter has a predicate saying, well, I only accept elements that do not have the value 3. Passed here as a lambda. OK. What is going on here? What is going on here is that on top of the collection, you place a view, the filter view, which just refers to the collection and has this predicate saying, I don't accept 3s. So the effect is interesting. The effect is so that we say, well, look at this example. This shows a little bit in more general way the effect. So we have a slightly different vector, 1, 8, 15, 47, 11, 42, and we search for the elements greater than 40. The idea is, as a vector has an API to provide iteration, to support iteration, and then the iterators you can use by calling plus, plus, and star, and other operations, depending on the category. For a filter, we have the same. The filter refers to the container and provides the same interface. Now, if the range-based for loop calls begin here, then we go to the view. The view says, oh, you want to have the first element? Good. Now, let me tell you that. I will find it on my reference collection. That's begin. But wait a minute, we have a filter here. The first element I cannot accept. So that's not valid. So you ask for begin. You want me to give you the first element. Well, what I call is, I call begin to go to the first element and then go to the next element. Oh, that's an 8. Also not OK. 15. Also not OK. 47. Oh, yeah, that's it. That is what you return in this call, what the view returns as the beginning. What you get here is an iterator of the view. And the iterator of the view uses internally the vector iterator. So the same principle is still used, but it's hidden. Let's print the value. OK, let's print the value. We have the element. Go to the value. Print it. Let's go to the next element. Well, that's easy. We call plus plus. We have our iterator. And now the iterator has to continue to iterate in the vector to find the next element with a value greater than 40, which is 42. We can print it out, and we do that until we are, or as long as we are not at the end. That's how views operate. OK? In the design of a filter, there's an optimization. The optimization is once we found begin. So with the first call of the begin here, we say, oh, wait a minute, you know what? I might later on do another iteration over this collection. So let me cache begin. So because, yeah, processing, especially pipe processing, might mean afterwards there's a pipe element that calls begin multiple times. So we have multiple passes to iterate over the elements. So it would be expensive to iterate each and every time to the begin, especially if the begin is not right at the begin. So there's a consequence of that design. The consequence is, demos this example. It's an ordinary generic print function. In C++ 20, you can use auto instead of a template parameter. That's syntactic sugar. More interestingly is, yeah, we can pass a vector of int and a list of int. Good, we can print out the values. We pass the container by reference, const reference. So let's do what we just saw. Let's now iterate over the vector using this filter. Yeah, we create exactly the behavior we wanted. Now, when we iterate, we print out all the elements greater than 40. Awesome, works. Now, you call print with this pipeline. You get a compile time error. Oh, what the hell is wrong here? Well, you can see it, know it, if you carefully think about what I just told you. When print starts to iterate, it calls begin. Begin caches. Begin is cached. That means we modify the view. So as a result, this const here on top is an error, is a problem. So therefore, it works without passing to print, but it does not work when we use print. That has a couple of bad consequences. And it's even worse. There are other views where sometimes they cache, sometimes not. So when you print a vector and you say, let's skip the first 3 elements, that works. When you skip the first 3 elements and it's a list below, it does not compile. I consider this to be a design mistake of views. But it's important for you to know this. So you can also say, this is a feature. One last example, what the consequence of this feature is. Let's define that we only want to have from a collection all the elements that are even. Let's iterate over them and use that to modify the elements, which is in principle allowed. Yeah, so 1, 4, 7, 10 becomes 1, 6, 7, 12. Awesome. Let's do it again. Awesome. Works. Good. Now let's add 1 instead of add 2. OK. 4 becomes 5. 10 becomes 11. We have no even elements anymore, so next time nothing happens. Oh. The 5 becomes a 6. But the 11 doesn't become a 12. Yeah, because we cached begin. So that's the first element we process. And then we look, is there anything else? None, is there? Yes, that's the standardized behavior of filters in C++20. It's not considered a bug. It's an optimization for multi-pass containers. And we know that this is a problem. So we say, this is undefined behavior. There's a caveat about the iterators of filters. And that says, modification to an iterator of a filter view is permitted, but results in undefined behavior if the resulting value does no longer satisfy the filter predicate. What? So this code is undefined behavior. You're writing a computer game. You want to iterate over all the monsters that are dead, and you want to resurrect them. That is undefined behavior, because resurrecting the monsters is breaking the predicate. We have intentionally designed the filter view in a way that one of the major use cases we use a filter for, which is fix the broken elements, has undefined behavior. By the way, that was not necessary. There's no need to cache. But that's something we discussed behind the scenes. That's a defined behavior. And I want to point it out that even in views, even in ranges, there are still iterators used a lot. And sometimes they have crazy behavior, intentional. The group who standardized this library does not think this is a bug. That's a feature because we make multi-pass iterations fast. Don't do that. That's a recommendation. I think you can hear that I'm not happy with that. Yes?
One question here. If you do a single pass, is that an undefined behavior, or is it just...
If you do a single pass, it works. That's the fun part. It works. Yes, but it's undefined behavior. There's a statement. So do it. And hope the best that nobody comes up with a very interesting way to implement this. Okay? But don't reuse the view. Use it always ad hoc, the filter. That's a benefit. OK, we are at the end. Iterators. It's a key element for the success of C++. We use them everywhere where we have more than one element. It's a glue code between ranges and algorithms. And that's still true even with ranges and views. It's a pure abstraction. Everything that behaves like an iterator is an iterator. Different categories are provided, so different iterators have different abilities. Usually, in general, iterators do not know their ranges. For that reason, they don't know where the end is. They cannot insert or remove elements. Use iterators with care because they have reference semantics. They refer to something. That something still has to exist. And if you compare to iterators, they should refer to the same range. And iterators of C++ 2x filters and other views cache, which has some interesting consequences. Yeah, I know my time is over. Do we have time for one question? One. Is there any question? So otherwise it might be completely compelling. Yes, hi.
What's the rationale for removing derivation from std iterators? There's a microphone.
Yeah. Otherwise I would have repeated the question, but thanks.
Why did they remove the ability to derive from std iterator and make us declare everything to make a custom iterator?
So what the person you're asking is saying indirectly is there was a base class called std iterator. Well, this base class was only syntactic sugar to make the definition a little bit easier. It was never required to have it because all we require is behavior, not a specific base class. And there were some issues with that. So that's why we did that. No big deal. Good. That was the last question. I hope you learned something about iterators. I hope you're not too frustrated about C++ 20. A lot of good things are there. And yeah, it's challenging, and it's still challenging to use C++. Let's hope the best. Enjoy.